Hello everyone. In this section we will cover bond enthalpies and how to use bond enthalpies and average bond enthalpies in order to calculate enthalpy changes of reactions as we did with enthalpy change of combustion and formation values. But in this section we will use bond enthalpy values. This is section 5.3 as stated here, bond enthalpies and average bond enthalpies. In this first video I will start to explain what is bond enthalpy and what is an average bond enthalpy. And in the next videos, I will teach you how to use them in order to calculate enthalpy changes of reactions. It's stated here, the definition of bond enthalpy. Bond enthalpy is the enthalpy change when 1 mole of gaseous covalent bonds is broken under standard conditions. Two words you should note here is the word gaseous, as seen here, gaseous covalent bonds, and broken. Thus, I'm going to read it again. Bond enthalpy is the enthalpy change when 1 mole of gaseous covalent bonds, so the covalent bonds must be in the gaseous state, and I will explain why in a bit, are broken, not formed, are broken under standard conditions. I have an error here. Under standard conditions. My apologies. Standard conditions. Why they should be in the gaseous state? Why before breaking bonds, in order to measure the energy required to break a covalent bond? This is what the definition states. It's the energy required basically to break 1 mole of gaseous covalent bonds. It has to be in the gaseous state. The reason for this is as follows. I'm going to use the example of bromine, for example. So if we get Br2 liquid, as you see here, if you heat bromine, this is in its standard state, bromine exists as a liquid. Thus, if we supply it with heat energy, the first part of the heat energy will be transferred to break the intermolecular forces between the Br2 molecule and convert it into Br2 gas. Thus, this would represent the delta H of vaporization, or in other terms, the energy required to break the intermolecular forces, which in this case are London dispersion forces between the molecules, to break them apart. After it's converted to Br2 gas, any energy you supply after this will go to break the covalent bonds. Thus, this energy here will go to break the Br-Br bond. Therefore, you cannot use Br2 liquid in an equation and use its bond enthalpy, because this wouldn't represent its bond enthalpy, because to convert Br2, to break Br2 into gaseous atoms, thus breaking the covalent bond, involves two processes. First, to vaporize it. Some heat will be supplied to vaporize it, and then the second part, the heat supplied in the second part here, will go to break the covalent bond. And thus, if you add both, this wouldn't represent the enthalpy change required to break 1 mole of gaseous covalent bonds. On the other hand, it would represent two processes, which is the first being delta H vaporization, and the second being the energy required to break 1 mole of gaseous covalent bonds. Therefore, when we want to measure the bond enthalpies for any molecule, they must be in the gaseous state, because once they are in the gaseous state, any energy supplied to them at this point will go to break the covalent bonds. But prior to this point, the energy won't go to break the covalent bonds, as I showed in this example here. Therefore, they must be in the gaseous state. The other word you need to notice is broken. To break a covalent bond requires energy, because these two atoms are bonded and they are stable, and thus to break them apart, we need to supply them with energy to form unstable atoms. On the other hand, bond forming is an exothermic process, since these unstable atoms, when they form a bond, they become more stable, thus releasing energy. This is stated over here. I've stated that bond breaking requires energy, which is an endothermic process, while bond forming releases energy, which is exothermic process. I've also noted here that bond enthalpies are used you can use bond enthalpies to calculate enthalpy changes of reactions that occur in the gaseous state only. Thus, the reactants and products must be in the gaseous state, because these values are determined for reactants and products in the gaseous state. To write an equation to represent this process as we did with the enthalpy change of formation and enthalpy change of combustion. Thus, this is a good example here. I've used hydrogen, H2. Thus, it's already in the gaseous state, as you can see here. Thus, any energy we supply to it at this point will go to break the bonds. And thus, this is what it looks like. Initially, we took this in topic 4 bonding, hydrogen bonded with a hydrogen in the gaseous state. Any energy we supply to it will go to break the bond, and thus this bond will break, forming one H gaseous atom and another H gaseous atom as displayed here. Thus, this represents the enthalpy change required to break 1 mole of gaseous covalent bonds under standard conditions. I've used another example here, HCl in the gaseous state once again. HCl in the gaseous state. If we supply it with energy, the energy will go to break the bonds, and thus HCl when bonded looks something like this, H bonded with Cl, and thus any energy we supply will go to break the bonds, thus forming gaseous atoms, one H gaseous atom and one chlorine gaseous atom as shown here. Thus this represents the energy required to break 1 mole of gaseous covalent bonds to form gaseous atoms. As in this example here, the energy goes to break 1 mole of gaseous covalent bonds. In this case, it's an HCl bond to form gaseous atoms. This represents the hydrogen bond enthalpy, the energy required to break this bond, and this equation represents the HCl bond enthalpy as written here. You should notice that the definition states that the bond enthalpies are measured when breaking covalent bonds, and since bond breaking is an endothermic process, thus all the values noted in the data booklet for bond enthalpies would be positive values. Its delta H would be a positive value because it's an endothermic process. If one were to require the bond forming, the energy for forming a bond, you would simply take the value in the data booklet and flip its sign, since bond forming is exothermic, and thus its enthalpy change sign would be a negative. I've attached the data booklet table for bond enthalpies. This table is table 11. As you can see here in the data booklet, it states bond enthalpies and average bond enthalpies, which we did not discuss yet. We will discuss in a bit. They show you the bond enthalpies here. If you can notice that all these values are positive because this is the energy required to break a bond. For example, in my first equation there, the energy required to break 1 hydrogen bonded with another hydrogen here, the value would be 436. Thus, I'm going to circle these to be more clear. Thus, the enthalpy change to break 1 mole of gaseous hydrogen-hydrogen bonds would be 436. Which is a positive value here because this is bond breaking. If you require the bond forming, the amount of energy released when this bond is formed, you simply change this sign to a negative. We've also seen HCl in the example. There's hydrogen and there's chlorine here. And that's the value to break this bond in the gaseous state is 431. This is how you use this table, and they're all listed as positive value because these are the values for breaking bonds, not forming them. These are all for single covalent bonds. For multiple bonds, the multiple bonds are listed down here, and this is the carbon-carbon delocalized bond in benzene right there, as you can see. These are multiple bonds as well as the delocalized bond in benzene, which are also positive values because this is the amount of energy required to break these, a bond. 1 mole of gaseous covalent bonds. Thus, I will go back to this first statement here. Enthalpy changes of reaction occurring in the gaseous state, as I discussed, in the gaseous phase, can be worked out if we know the amount of energy required when bonds are broken in reactants and the amount of energy released when bonds are formed in the products. I will discuss this in videos to come, but the cycle that you will use will involve initially breaking all the bonds in the molecules in the reactants, which would be in the gaseous phase because you're using bond enthalpies, breaking these bonds to form gaseous atoms. which is an endothermic process, and then these gaseous atoms would combine in a different way to form the products, but this process is bond forming and thus would be an exothermic process. Thus, if we know the values for the bond enthalpies required to break all the bonds in the reactants and the bond enthalpies required to form all the bonds in the reactants, we can figure out the enthalpy change of a reaction occurring in the gaseous phase, as we did with enthalpy changes of combustion and formation, which I will cover in the next video. We've discussed what bond enthalpy is. Thus, it's the energy required to break 1 mole of gaseous covalent bonds under standard conditions. On the other hand, these values here are bond enthalpies, not average bond enthalpies. And I've discussed why bond enthalpies are used for reactions occurring in the gaseous state only. This is because the bond enthalpies are measured for gaseous covalent bonds. And thus, if you were to use bond enthalpies to calculate enthalpy changes of reactions, you would be required to all the reactants and products must be in the gaseous state. Otherwise, you cannot use bond enthalpies to calculate the enthalpy change of reaction. I've stated here, bond enthalpies are defined in terms of breaking bonds, as I just discussed, which requires energy, and therefore all values in table 11 in the data booklet have positive values. And if we require bond forming values, we simply change its sign into a negative sign to convert the process into an exothermic process for forming bonds. Another definition you need to know, these two definitions are actually asked on exams, regularly asked. This is the definition for bond enthalpy. It's the enthalpy change in 1 mole of gaseous covalent bonds. It's broken under standard conditions. While for the average bond enthalpies, I will discuss what an average bond enthalpy is, and then I will read the definition listed below here. The examples I showed above for hydrogen bonded with hydrogen, for example, you can never find hydrogen bonded to another hydrogen except in this H2 molecule. You would never see a carbon bonded to a hydrogen bonded to another hydrogen. This does not happen. Thus, you can only find a hydrogen bonded with a hydrogen in H2 gas. And thus, this would only have one value, which is the bond enthalpy of H2 when we break this bond. On the other hand, some bonds are present in many different molecules, unlike H2 here, unlike the two HH bond here. The CH bond is present in many different molecules as shown here. This is an ethane molecule. This is an ethanol molecule. This is ethanol, and this is benzene, all of which contain CH bonds. If you were to measure the bond enthalpy in the gaseous phase for the CH bond in C2H6, this compound here, it would slightly differ from the CH bond in this compound here, which is ethanol. Since these carbon-hydrogen bonds are not in the same environment as these ones, due to the C double bond O here, which would represent some repulsive forces which would affect the bond enthalpy of this carbon-hydrogen bond and these two. Thus, these carbon-hydrogen bonds, the value of the bond enthalpy in this molecule will differ slightly from this one, as well as this carbon-hydrogen bond here in benzene. Thus, since we have variable bond enthalpies for these carbon-hydrogen bonds, what was done was they were averaged over several similar compounds to produce a bond enthalpy for the carbon-hydrogen bond. And thus, this is not a bond enthalpy. This is an average bond enthalpy. Allow me to read this paragraph here. Some bonds have average bond enthalpy values. For example, the CH bond energy in ethane, this compound here, slightly different from that in benzene due to repulsive forces, as I discussed, since they are in slightly different environments relative to neighboring groups, and thus the value quoted in the table for the CH bond is an average value, averaged over the values of CH bond in many similar compounds. Thus, the definition for average bond enthalpy would translate as follows. Usually, 2 marks will be required or awarded for this definition. I will show you why. It's the first part of the definition is the exact same definition as bond enthalpies. It's the average bond enthalpy. Normally, in that first definition, we stated is the enthalpy change when 1 mole of gaseous covalent bond is broken under standard conditions. The only difference here was we added the word average. Uh, the word average was added. Thus, it's the average amount of energy required to break 1 mole of gaseous covalent bonds under standard conditions. You would be awarded 1 mark for this. To be awarded the second mark, you need to explain what you mean by the word average, which I explained here, averaged over several similar compounds. Thus, the definition for average bond enthalpy is the average amount of energy required to break 1 mole of gaseous covalent bonds under standard conditions, which is averaged over several similar compounds. This would award 2 marks. Thus, normally, the average bond enthalpy is awarded, definition is awarded 2 marks. If I were to represent the average bond enthalpy using an equation, using CH4 as an example, methane gas, this equation here does not represent the definition. I put it as an example when they try to trick you with this, because as you can see here, this is CH4, and if I were to draw CH4 here, CH4 contains 4 CH bonds, and thus to produce 4 gaseous hydrogen atoms and 1 gaseous carbon atom, you would have to break 4 moles, not 1 mole, 4 moles of carbon-hydrogen bonds, and thus this would represent the bond enthalpy multiplied by 4. But the definition states it's the energy required to break 1 mole of gaseous covalent bonds. As displayed here, this is the drawing. Thus, if you were to calculate, if I was to write an equation to represent the average bond enthalpy, since this represents 4 CH bonds, I would divide this equation by 4. And thus this equation is divided by 4, so that it would represent 1 CH bond as shown in this equation here. This would become 1/4 of a CH4 molecule in the gaseous state, would produce 1/4 of a carbon gaseous atom plus 1 hydrogen gaseous atom. This would represent the definition of average bond enthalpy as stated here. This is the definition. Thus, it's averaged over 4 in this case to produce 1 mole of CH bonds. I've restated this here. Average refers to the fact that the bond enthalpy is different in different molecules. The same bond enthalpy is different in similar molecules, let's say. And therefore the value quoted is the average amount of energy required to break a particular bond in a range of similar molecules. Thus, average bond enthalpies are really not as accurate as using enthalpy changes of combustion or formation values, since those values are determined experimentally, while these values are averaged over several similar compounds, and this is what I've stated here. Average bond enthalpies can introduce some accuracies into calculations, since they are averaged over several similar compounds and are therefore more accurate when they involve breaking or making only a few bonds. They would be somewhat accurate, but still they would always be less accurate than enthalpy changes of reactions determined using enthalpy change of combustion and formation values, as we learned previously. This is just an introduction video to explain what bond enthalpies are and what average bond enthalpies are. Their definitions should be memorized or at least understood. And you should know that bond breaking requires energy, which is an endothermic process. Bond forming releases energy, which is an exothermic process, as stated previously. And the values in the data booklet are quoted for bond breaking. Thus, if one were to require the bond enthalpies required to form a bond, we would flip the sign in the data booklet to produce a negative enthalpy change of reaction, which is an bond enthalpy, which is an exothermic bond enthalpy. In the next video, I will explain how to use bond enthalpies and average bond enthalpies to determine enthalpy changes of reactions using methods 1 and 2, as we previously covered. Method 1 being an energy cycle, and method 2 being the general mathematical equation, which I prefer you using in exams. Please watch the second video. Thank you for watching.